Ever feel like someone's trying to pull a fast one with, like, sneaky wording? You know, like when a politician promises a clean government, and you're left thinking, okay, what does that even mean?
It's like those shoe commercials, right? The ones that
Mm,
promise to make you intelligent. Yeah, they put it in a sentence, but that doesn't make it true.
exactly. And that takes us right into today's deep dive, the power of proof. I got some excerpts here all about mathematical proofs, and I'm honestly a bit intimidated, but hopefully by the end of this, we could decode this stuff.
Oh, and before you get those math class flashbacks, trust me, this is relevant to everyone. We're not just talking about equations here. This is about thinking clearly, building a solid argument. It's actually pretty satisfying when you get the hang of it.
Okay, so let's unpack this. The text starts with mathematical statements. Basically, any claim that's either always true, always false, or somewhere in between, like a bit wishy-washy.
Yeah, and it's the wishy-washy ones that can really trip us up. Like they use the example vehicles have four wheels. True for some cars, sure, but definitely not for my motorcycle. So yeah, that just shows how crucial precise language is. For any solid argument, really.
Right, right. Like when people say, well, people from X are all good at Y. Way too broad. You need those specifics. You need to know what makes someone good at something before you can even begin to make a judgment call.
Exactly. You've got to break it down. Now, the text then gets into deductive reasoning. Sounds kind of fancy, but it's really just about connecting the dots, following the logic.
So that, like, if we know all cats are mammals and Fluffy is a cat, bam, Fluffy has to be a mammal. No way around it.
Precisely. It's like a chain reaction. But the tricky part is sometimes those links in the chain are hidden. They're implied. Like the text uses the example of a parallelogram. Remember those from geometry? It might not be explicitly stated, but opposite sides of a parallelogram are always equal. That's just a fact.
Geometry flashbacks. But it makes sense. One piece of information unlocks others. Like if you know one side of that parallelogram is 10 centimeters, well, the opposite side has to be 10 centimeters too.
Exactly, and that leads to a crucial point. Mathematicians hate uncertainty. They don't just want to see a pattern in a few examples. They want proof that it works for every single case.
It's like that formula for adding numbers, 1 plus 2 plus 3 and so on. You can test it out with different values, sure, but how do we know for sure that it works for any number, no matter how big or small?
That's the million-dollar question, and that's where proofs come in. They're not just about showing what is true, but why it must be true, no matter what. No exception.
Okay, so how do they actually build these ironclad proofs?
Mm.
What's the secret sauce?
Well, they've got a few trusty tools up their sleeves.
A few trusty tools up their sleeves, huh? Sounds intriguing. It's like we're about to unlock the secrets of a master craftsperson, but instead of wood or metal, we're working with pure logic. So spill the beans. What's the first tool they pull out of their logical toolbox?
Well, imagine a builder, right? They start with a solid foundation and then carefully lay bricks on top of each other to build a house. The first proof method, the direct proof, is kind of like that. You start with something solid, something you already know is true, like those established facts and definitions, and then you just build on top of that, step by step, until you reach your conclusion.
So, solid foundation, solid logic, solid proof. Makes sense. But I'm a visual learner. What would a direct proof look like in action? Got any examples?
Of course. The text uses the example of proving that when you add two rational numbers, the result is always another rational number. Picture it this way. You've got two pizzas. You cut one into thirds and the other into quarters. Now, no matter how many slices you take from each pizza, you can always express the total amount of pizza you've eaten as a fraction of the whole pizzas, right?
Yeah, that makes sense. You're just adding up fractions.
Exactly. And because rational numbers are, at their core, really just fractions, you can be sure that adding any two of them together will always give you another fraction, another rational number. It's like, no matter how you slice it, pun intended, the result is going to be rational.
Okay, I'm with you. So that's direct proof.
Okay.
Start with the knowns and build your way up. But what about this proof by exhaustion thing? Does that involve, like, comfy chairs and lots of snacks? Because, I'm always up for a good snack break.
Well, I hate to disappoint, but no comfy chairs or snacks with this one. Proof by exhaustion is less about relaxing and more about, well, being exhaustive. It's like when you lose your keys and you have to check every single corner of your house until you find them. It's not always the most elegant method, but sometimes it's the most straightforward. You systematically rule out every other possibility until you're only left with the one you're trying to prove.
So it's like no stone unturned. You're basically saying, okay, if it's not here, and it's not here, and it's not here, then it must be here.
Precisely. And the text actually uses the example of prime numbers. Those numbers that are only divisible by 1 in themselves. Well, there's a proof by exhaustion that shows that any prime number greater than 3 can be written in one of two forms, 6k plus 1 or 6k plus 5, where k is any integer. It's a bit tedious, but by carefully considering all the possibilities, we can be absolutely certain about our conclusion.
Okay, I see. It's thorough, if nothing else. So we've got direct proof, where you build up to the conclusion, and proof by exhaustion, where you eliminate all other options. It's like build it up versus narrow it down. What other tools are we working with here?
Okay, so now for my personal favorite, and it's a bit of a mind bender, proof by contradiction.
Proof by contradiction. Okay, lay it on me. What's so mind-bending about this one?
Well, with proof by contradiction, you start by assuming the opposite of what you're trying to prove. I know it sounds counterintuitive, right?
Wait, really? That seems completely backwards. Why would you start by assuming the thing you're trying to disprove?
Because sometimes the best way to show something is true is to demonstrate just how ridiculously wrong the opposite would be. Think about it like this. Imagine someone claiming the Earth is flat. Now, we could try to directly prove them wrong, but with proof by contradiction, we take a different approach. We start by assuming they're right, that the Earth is flat, and then we follow that logic through and see where it leads us.
And I'm guessing it leads to some pretty wacky conclusions, right?
Exactly. If the Earth were flat, it would contradict a whole bunch of things we already know to be true about gravity, about ships disappearing hull first over the horizon, about circumnavigation. By assuming the opposite, we stumble upon these contradictions, these impossibilities, and that's how we know our initial assumption that the Earth is flat has to be wrong.
So it's like setting a logical trap. You lure the argument into this trap by assuming the opposite, and then bam, it self-destructs because it contradicts everything we know.
You got it. And the text uses a really cool example of this with rational and irrational numbers. They're trying to prove that when you multiply a non-zero rational number by an irrational number, the result is always irrational. So they start by assuming the opposite, that the product is actually rational, and then they carefully follow that line of reasoning step by step until they hit a wall. A contradiction pops up, showing that their initial assumption that the product could be rational just doesn't hold water.
It's like a mathematical plot twist. You think the story's going one way, and then bam, contradiction. And that's how you know the original assumption was off base.
Yeah.
I'm starting to see why this one's your favorite.
It's elegant, it's powerful, and it really highlights that sometimes the most unexpected approaches can unlock the deepest truths.
This is blowing my mind. Okay, so we've got direct proof, we've got proof by exhaustion, and we've got the mind-bending proof by contradiction. Are there any other methods in this mathematician's arsenal, or have we pretty much covered the basics?
Well, those are some of the big ones, for sure. But the adventure of logic doesn't stop there. The text also dives into the wonderful world of negations and converses. And let me tell you, these are all about the details, the nuances of how we phrase our arguments.
Negations. Converses. Okay, I can already tell things are about to get even more interesting. It's like we're leveling up in this logic game. But before we dive into those, I think we need a quick breather. We'll be right back after this short break to unravel the mysteries of negations and converses. Don't go anywhere. All right, so we're back and ready to tackle these negations and converses. I'm already feeling like I need to be extra careful with my words here. Like one wrong step and the whole argument explodes.
It's true. These concepts really highlight the power of language and how even a small change in wording can completely change the meaning of an argument.
Yeah, and speaking of word changes, let's start with those negations. You made it sound like it's not as simple as just adding a not. So what's the catch?
Well, think about the example from the text. The statement is, all teachers are female. Now, if you just tack on a not at the beginning, you get, not all teachers are female. Which, okay, that's technically the negation, but it could be clearer.
Okay, I see what you mean. It's like, are we saying some teachers are male or all teachers are male? There's a subtle difference there.
Exactly. And that's where things can get messy. Instead of just adding not, it's about finding a statement that expresses the true opposite meaning. So instead of not all teachers are female, we could say some teachers are male. It's more direct, more precise.
Ah, okay. So it's not just about adding a word. It's about capturing the opposite idea. Precision is key, which I'm sensing is going to be even more important for those converses you mentioned. They sounded like a whole other level of tricky.
Think of it this way. A statement and its converse are like two sides of the same coin, connected but different. Like, take the statement. If it's raining, then the ground is wet. Pretty straightforward, right?
Yeah, I'd say that's generally true, unless you're using some kind of fancy hydrophobic pavement, but that's a whole other story.
Exactly. But now let's flip it and look at the converse. If the ground is wet, then it's raining. Still true.
Not necessarily. I mean, my sprinklers make the ground pretty wet, and I haven't seen a rain cloud all day.
Exactly. Just because the original statement is true doesn't mean the converse is automatically true as well. Could be sprinklers, could be a burst pipe, could be, well, all sorts of things. We have to examine each statement on its own merits, separate from the other.
So it's like one of those optical illusions. Your brain sees a connection, but then you have to take a step back and be like, hold on, is that really what's going on here?
Perfectly put. And this concept, these converses, they pop up everywhere, not just in math. Like you'll often hear people say, if you're successful, then you work hard, implying that all successful people are hard workers.
Right. The classic hustle culture mentality.
Exactly. But then look at the converse. If you work hard, then you'll be successful. That's a whole different ballgame.
Yeah, and unfortunately, not always true. There are plenty of hardworking people out there who haven't quite achieved the success they deserve. It's a lot more nuanced than a simple if-then statement.
Precisely. And that's the beauty of this whole deep dive. It's made us think critically about how we use language, how we construct arguments, and how easily we can be misled by seemingly straightforward statements.
It's like we've been given this secret decoder ring for logic, and suddenly we're seeing the world in a whole new light.
I love that analogy. And the best part is these skills, this critical thinking, it's applicable everywhere. From deciphering political speeches to evaluating the claims in those shoe commercials, it's all connected.
Absolutely. So, to our listeners out there, next time someone throws out a truth, remember what we've learned today. Don't be afraid to channel your inner mathematician, ask those tough questions, and don't just take things at face value.
Yes. Question everything, analyze those arguments, look for those hidden assumptions, and remember, even the most convincing statements might have a converse lurking beneath the surface.
I couldn't have said it better myself. A huge thank you to everyone for joining us on this incredible deep dive into the world of logic and proof. It's been an eye-opening journey, and we hope you've enjoyed it as much as we have. Until next time, stay curious.